We have a quiz about root locus next week, but I'm still confused about it.
Me too. I didn't get this lesson well.
The doctor is offering office hours today. Let's go and see him.
Okay. By the way, when is the office hours?
It starts in 5 minutes, so let's go. Hi, doctor.
Oh, hello. How can I help you?
We're still a little bit confused about the root locus. Would you please explain it to us more?
Yes, of course. So, to make it easier, we will go through it step by step. In the beginning, you need to know the definition of a root locus. It's a graphical presentation of the closed loop poles as system's parameter is varied. From root locus, we can analyze and design for stability and transient response. Here's a feedback block diagram where K represents the gain, G of S represents transfer function, H of S represents feedback transfer function. And this is the equivalent transfer function. The characteristic equation in this case is G of S times H of S.
But what is a gain?
Good question. The gain is the amplification factor. The closed loop poles change with the changes in the system gain. It changes location as the gain K is varied. This plane represents the path of the closed loop poles as the gain is varied. And that's what we call a root locus. After understanding the main concept of root locus, it's time to learn how to sketch it. There are 9 steps to follow to sketch root locus. First, we will find the number of branches. A branch is the path that one pole traverses. The number of branches is equal to the number of closed loop poles, which equals to 4 in this case. Moving on to the next step, symmetry. So the root locus is symmetrical about the real axis. So the next step is the real axis segments. It's a segment that connects poles and zeros. On the real axis, for k is greater than 0, the root locus exists to the left of an odd number of real axis, a finite loop poles or finite open loop zeros. Poles are represented with x, zeros are represented with a circle. The root locus begins at the finite and infinite poles of g of s and h of s, and ends at the finite and infinite zeros of g of s and h of s. The root starts at the open loop poles and ends at the open loop zeros. So the next step is to know how the root locus behave at infinity. And to know that, we need to find the asymptotes. First, using this equation where k is equal to 0, plus minus 1, plus minus 2, and plus minus 3. Q is equal to the number of finite poles minus the number of finite zeros. You will notice that the angles will keep repeating as the k is increasing. The real axis intercept can be found using this equation. The angles of the lines will intersect at this point. The line will be parallel to the asymptote. To understand how to refine the sketch, we will look at another example. In this example, we can calculate the breakaway and break-in points.
But how can we find these points?
First, we need to find the derivative of the denominator and the numerator. Plug them into the equation and find the roots. To further refine the root locus, we will find the imaginary axis crossing. You can do that by using a root table. Forcing the first row to equal 0 will yield the gain value. Then taking the even polynomial equation and the gain value and solving it to find the roots. Finding the angles of departure and arrival. If we have a pole, we assume all angles drawn from all other poles and zeros are drawn directly to the pole. Then we find the sum of all the angles, negative for the poles, positive for the zeros, and set it equal to 0.
But what if it was a zero pole?
We will do the same steps, but we get the angle of arrival.
Thank you, doctor, for your time.